Okay, so let's start today's session. Yeah, okay. So, a very good afternoon, everyone, all who have joined. So, this is fifth week, fifth interactive session for NPTEL course Solid State Physics, where the course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a teaching assistant for this course. I am Renalini, PMRF Research Scholar from School of Physics, University of Hyderabad. And we have these sessions every Saturday, 3 to 5 p.m., where we discuss that week's topics, as well as we do some assignment problems so that it will help you guys do your weekly assignments, as well as help you in taking up the exam at the end. Okay, so with that, let's start and have some recap of what we discussed last week. These are the recommended books. We have already talked about them. Yeah. So last week we had started discussing about X-ray diffraction technique, which is a very important experimental technique when we talk about understanding materials, be it in chemistry or physics. We understood how we get the X-ray diffraction condition, which is that Bragg's law we call. We had seen how we have different planes, crystal planes, and then we have interplanar spacing, and we tried to derive this Bragg's law, which is 2d sine theta is equal to n lambda. We know what these parameters are, we had discussed. And we had also discussed why we use X-rays for this, for understanding these materials, and not via any other electromagnetic wave. And after this, so we had discussed how we get the X-ray waves, X-ray source, that we use some metal, hit it with highly energized electrons, and then there is some physics. After that, we get particular, in some range, we get these energies emitted, and if we want particular wavelength, then we use a filter, and thus how we get particular wavelength of X-ray, right? So we discussed about how we generate X-rays, then we have discussed what is the physics behind getting X-rays, like when we have atom, right, and the highly energized electron, when it hit the K shell electron and knocks it out, then the electron from the next L shell or M shell, when they come and fill up this vacancy, then the difference of energy is given out in form of this X-rays. This is basically how we get X-rays. And then we were discussing the different techniques like Bragg's treatment, Lave's treatment, and then of course, after the derivation of how we get this Bragg's condition of diffraction. Then we had discussed Lave's method, where the theta is fixed and wavelength of X-ray, we use white X-ray, where different X-ray wavelengths are used. And then we have another method. So we had discussed one was Lave's method, where theta is fixed and lambda, we don't have one particular wavelength, but a range, and that's why we call it these white X-ray, because it has various wavelength. Another method we discussed was rotating crystal method. Right here, the theta we vary by rotating the sample, and here we use particular wavelength of X-ray. And then another powder method, where we grind the sample into powder so that different crystal planes get exposed to the incident X-ray. Here also we keep theta variable, we rotate the powdered sample, and we use particular wavelength, which usually, like the very popularly used, is copper K alpha, which is 1.54 angstrom. This is very much used in usual uh, material characterization. Okay. So these were the different things we had basically discussed last time, and then we did some questions based on this Bragg's condition and other different problems also. Now moving on from this, we have another interesting thing that was discussed this week, which is reciprocal lattice. So before directly going to reciprocal lattice, let's start with understanding what we have in real space. When we talk about real space, the space we have been talking till now, we didn't name it, but whenever we were talking about our unit cells, or whenever we were saying we have this XYZ coordinate which are perpendicular to each other, and then we were defining planes and directions based on them. So all that we were talking in real space, the space that we can see around, even if it's atomic level, all that is in real space. Okay, and that name was started when we defined something known as reciprocal space. Okay, so this real space, we in this real space, the lattice, any lattice that we have, we call it real lattice or direct lattice. Okay, these are the different names. And the direct lattice or real lattice is defined by these unit vectors, XYZ unit vectors, because in direct lattice or real lattice we were talking about translation vector, right? Like whole discussion had started that these lattice point, the pattern, when it's repeated, we get the whole lattice or the whole crystal. So the translation vector, like some number, say like this. So like this lattice, when taken with A x cap, depends what kind of pattern we have, then accordingly A, B, C, which are numbers, integers, they will have particular value, and then following that translation we'll get that whole lattice or whole pattern. So the indirect real space, when we were talking about direct lattice or real lattice, we had this translation vector which were defined by these primitive vectors, primitive unit, these direct vectors, or if we are talking about primitive unit cell, then primitive unit vectors or basis vectors also we call them, right? Because to every lattice point, when we associate group of atoms or single atom, and then that is repeated, we get crystal. So again, in real space, our real lattices or direct lattices are defined by, when we talk about primitive unit cell, they are defined by primitive basis vectors. Okay, and primitive unit cell, we know number of atoms in that unit cell net should be 1. So like simple cubic, when we talk in 3D, we have simple cubic in which all the atoms are at the corners. This also we have discussed how they get shared, and so the effective contribution of one corner atom is 1/8 in particular unit cell, and since there are total 8 atoms, so the net contribution is 1. So this is a primitive unit cell. Whereas if we talk about say BCC unit cell, then the cell usually we every time draw to understand. We have atoms at the corners, all the 8 corners, so their contribution is 1. Then we have 1 at the body center. This is how we have always been known BCC structure, that 8 atoms at the 8 corners and then 1 atom at the body center, right? 1 at the body center, so total 2. That means this way that we know body centered cubic crystal, this is not primitive because this has 2 atoms per unit cell, and the very definition of primitive unit cell is that there should be 1 atom per unit cell. So we'll see in today's session how we can get a primitive unit cell for BCC also, and same we'll do for FCC as well. So okay, so these, as I said, these are not primitive because there are more than 1 atom in this unit cell. So that's why we came up with the name that this is not primitive but conventional unit cell. That whenever we talk about BCC, whenever we talk about FCC, we draw these particular way. We understand whenever we have to find out packing fraction or neighboring coordination number, like neighboring atoms, we keep these picture in mind. That 1 atom at the center, 8 at the corners. For FCC, we have 6 faces, 6 atoms on the faces, and then 8 at the corner. So total is like 4 per unit cell. So these are not primitive unit cell, but they are conventional unit cell. We call them conventional unit cell. Okay. So till now, the way we have been discussing about BCC, FCC, they were actually conventional unit cell and not primitive unit cell. Just to make you clear about this. Okay. Now, as I said, to define these primitive unit cells, we need unit vectors in real space or direct lattice space. We, like, say if my lattice vectors are A1, A2, A3, any way we can represent. Either I can say this or I can say X, Y, Z. All it means is the 3 orthogonal lattice vectors. Okay, this is my primitive unit basis vector. Now this is in direct space, that also we have understood, because in direct space we have lattice arrangement and everything. Although just to emphasize that even the lattice, we defined it is mathematical concept. We don't actually have points, right? That is just mental framework. And in reality, we have atoms or group of atoms on those positions. So yeah. So this was all in direct space or real space. Now, another set of basis vectors have been defined, okay, such that they are related with the direct lattice, direct or real lattice. Okay, they are related with these lattice and thus the lattice vectors also, and we call them reciprocal lattice. We'll see why we call them reciprocal lattice or reciprocal space, but they are very much related with these real space, and there is a reason that we even came to define them, or we came to reciprocal space or reciprocal lattice, because in some cases they make our life easier to understand certain things. So they make things easier to visualize, easier to understand. That's why we came up with this by a lot of scientists who work in this area. But now let's just understand this by seeing that we had some lattice arrangement in real space, and then related to that we defined something, some another set of basis vectors, and we call them reciprocal basis vectors. Okay, and we define these for these we have A1, A2, A3. Here we define them as, if we are using A1, A2, A3, then either we can call A1 star, A2 star. Usually we use this denotation. Otherwise, B1, B2, B3, anything is okay. And then, as I said, they are related. We defined it from this. Then, how are they related? Okay, what is the relation? So, the relation is given as that, let's say, the reciprocal lattice vector AI star, okay, that its dot product with real lattice vector AJ is equal to delta IJ. If you guys are aware, then good. Otherwise, I'll tell this delta IJ. What it means is when I equals J, then this delta IJ is equal to 1. And when I is not equal to J, this delta IJ is 0. So the relation, if I write this thing, will mean this: A1 star dot A1 is equal to 1, A1 star dot A2 is equal to 0, A1 star dot A3 is equal to 0, A2 star, these A1, A2, A1 star, A2 star, A3 star are all reciprocal lattice vector. Just now, like we came up with, like we introduced, and we are telling how they are related with direct lattice vector. Okay, this is 0, A2 star, A2 is equal to 0, A2 star, A3 is equal to 0, A3 star dot A1, these are all dot products, A3 star dot A2 is equal to 0, A3 star dot A3 is equal to 1. So this is how we are defining that in real space we had these basis vectors, and then we are defining something known as a reciprocal space where we have these reciprocal basis vectors and they are related with direct space basis vectors through this relation. Okay, this clearly shows that they are reciprocal to each other, because we know when we have some dot product and the value is 0, because we know A dot B means A and B magnitude and cos theta, and we know cos 90 degree is 0. That means they are perpendicular to each other. And A1 cross A1 is parallel to each other. Okay. So construction of reciprocal lattice vector further. Okay, this is, we understood how they are related with direct lattice vectors. But how to get these reciprocal lattice vectors? As I said, till now it's not something that we came up with. Like we have, it's been constructed by various people like Ewalds and others who came up with this to understand something. So in the beginning, everything is kind of maths, but they all justify the things that we do in real space. That means whatever this mathematical invention has been done is true, is correct. It justifies whatever we see experimentally. Like we will see how in reciprocal space also we can get our Bragg's condition expression. So bear with me. So this is the relation, and then you must have seen in lectures also, I'm just writing the expression. Either for reciprocal, these reciprocal lattice vectors that I said, A1 star, A2 star, A3 star, how we define them. Usually we see these two. Either we just say A2 cross A3, where A1, A2, A3 are direct lattice vector. So from there itself we can construct the reciprocal lattice vector. And this is, in denominator we have volume of unit cell. Which unit cell? Direct space unit cell. So V is actually A1 dot A2 cross A3. So if I have a unit cell in real space, this is A1, or let's say A2, this is A3, and this is A1, then A2 cross A3 is this area of the unit cell, and when I take dot product with A1, then it means this whole volume. So volume of unit cell in direct space. Sometime it's also, there is a multiplication of 2 pi, so even with or without it, it's fine. So maybe in today we will discuss, so even without this, that's okay. The things won't change. This is just some adjustment constant. Sometime people use it, sometime we don't use it. Okay, so for A1 cross, this is the expression, like if I remove the 2 pi, and the next reciprocal lattice vector, again 1 by V, and then A3 cross A1, and A3 star, the third reciprocal lattice vector, will be given by 1 by V and A1 cross A2. So I hope this is clear. The A1, A2, A3 are direct space lattice vectors, and A1 star, A2 star, A3 star are reciprocal lattice vectors. We saw this is how they are related, and this is how we can get reciprocal lattice vector if we already know direct lattice vector. Okay. Now, as we just now discussed, that in real space we have these translation vectors which tell us how the lattice point will move to repeat itself and eventually give us the whole pattern. Like if we again talk about if it's linear, say, then, and say this is x, then my translation vector will be that I have to go 1 x and everything else will be 0. If I have a pattern like this, then either I can generate this whole thing, it's moving here, x direction, or it's moving y direction, or it's moving diagonally. Means x cap, some 1 x cap and 1 y cap and 0 z cap. This will be the translation vector here. So if this unit cell will repeat in this diagonal direction, it will repeat the whole lattice or something. So this is the translation vector that we define in real space. Now similar something we have in reciprocal space also. Reciprocal space also has something similar that we call reciprocal lattice vector, and we usually denote it this expression. This is a vector, so this arrow and star, because we have been using the star denotation for all the reciprocal lattice vectors as well, right? A1 star, A2 star, A3 star. Similarly, this is called reciprocal lattice vector. And now, okay, so we define this reciprocal lattice vector GHKL. We'll see why we are keeping this denotation, HKL plain denotation here. Okay, so this is how and it is also, we define it as, like we saw here, this translation vector was expressed in terms of these XYZ basis vectors with some integers as coefficient. Similarly, this will also be expressed as some coefficient of these reciprocal basis vectors, A1, A2 star, A3 star, okay, where HKL Here they were just some integers. In reciprocal lattice vector, these HKL are not random numbers. They are integers, of course, but they are related to some crystal plane in real space or direct space. So that HKL is what is giving this reciprocal lattice vector its expression. Okay, we'll see how. And the properties of these reciprocal lattice vector is that when we take its magnitude, it comes out to be this. Again, in derivation, for derivation you guys can check this week's lecture videos. We are just trying to understand and quickly revise. So just the expression that this is the magnitude of this reciprocal lattice vector is very interestingly, it comes the reciprocal of interplanar distance. You remember, right? When we have crystal planes like this parallel to each other, and they have some particular spacing between them. Like whatever the atoms are there on these crystal planes, they have some interplanar distance that we define by DHKL. For particular HKL, the interplanar spacing is 1, and like if it is some 100 plane, then the interplanar distance will be particular value, and if it's 111 plane, then the interplanar spacing will be different. So that's why we denote all these D's with some particular HKL. So this translation vector for 100, its magnitude will be the inverse of the interplanar distance of 100 plane. Similarly, the magnitude of reciprocal lattice vector for 111 corresponding to 111 plane will be inverse of the interplanar distance between 111 plane. So this is how they are related. This is the magnitude of reciprocal lattice vectors for particular HKL plane in real space. And another thing is that these vectors, they are perpendicular to these HKL planes. So these translation vectors, they are perpendicular to HKL plane in the real space. These HKL planes that we define using these Miller indexing, they are all in the real space. And when I am defining my translation vector in reciprocal space, we find that they are perpendicular to the HKL planes, and their value or the magnitude is inverse of the interplanar distance between those HKL planes. There is a very interesting relation between them. Now the next thing comes is understanding something known as Ewald sphere. Okay, so what happens is Ewald sphere, how we understand is, like just now I told that, okay, let's go there, just a minute. So what is Ewald sphere? Here in 2D, because we have a screen, so I'll just draw a circle and tell you, but when we are talking about 3D space around us, so it's actually not a circle but a sphere. So you have to keep that in mind, that we are talking about a sphere, not a circle. So if, like how this comes is, if we have some lattice vector defined like in this direction with this particular length, and like if I have some reciprocal lattice vector of some particular length ki, and taking one end of it I take as center and taking the tip as radius, if I draw a circle, okay, then in 3D it will be a sphere, in 2D I'm saying it's a circle. if I draw this sphere in 3D, taking this reciprocal lattice vector as radius, then I'll get a sphere, okay? And since this is in reciprocal space, so we will have reciprocal lattice also. And when I take this reciprocal lattice vector and make a sphere or circle, then these reciprocal lattices will be cutting this sphere, okay? And wherever it will be cutting, those points are of importance, because actually why this Ewald sphere concept also was introduced, to understand. If you remember in XRD we were talking about that we get some diffraction pattern, and on the screen or detecting screen we see some dots or some points. To understand them, this reciprocal space or this Ewald sphere concept was introduced by Mr. Ewald. And this one thing is this, that Ewald sphere is this sphere where we have some lattice vector as radius, and when we draw this sphere we get Ewald sphere. And in reciprocal lattice, wherever, if we have drawn a sphere like this and whatever points are cutting or lying on this sphere, those all points have some significance that let's understand now. So what we, like I told, we have Bragg's condition in real space that we saw how we derive it, and then we get 2d sine theta is equal to n lambda expression. The same way we have this in the same way we have this in reciprocal space, where what we say, instead of getting here, that if, say, this one lattice vector is my incident, like in real space we were saying this is my crystal planes, and this is interplanar spacing DHKL, and the X-ray is incident and then diffracting or reflecting from subsequent planes, right? And this was my incident ray, this was my reflected ray. The same way here, in reciprocal space, we define Ki is my incident ray, but here, since it's a vector, this Ki in reciprocal space, in real space I was just saying this is the direction of incidence. In reciprocal space, we define it, this incident X-ray, as a vector. That means it has magnitude as well as direction. Direction is the same as the direction of incident X-ray that we were talking about in real space also. And then this, if let's say this is the direction of X-ray incident on the lattice, okay, and then magnitude, from where the magnitude of this vector comes. So the magnitude is actually the inverse of the wavelength of XRD used. Wavelength of this lattice vector will be 1 over wavelength of the X-ray used. This is how we define this lattice vector, okay? Then if it is incident at some point, it will reflect also. This Ki, it has this direction, its wavelength is, its magnitude is 1 by lambda. Then after reflection, from Bragg's condition, we know after reflection it will go at the same angle, and this will be Kr, and Kr, its direction will be this, and its magnitude also will be 1 over lambda, because XRD is elastic scattering. It's elastic scattering or elastic collision of atoms and X-ray. That means whatever wavelength the X-ray had before colliding, after diffraction also it has the same wavelength. So magnitude will be 1 over lambda, the same. When this situation happens, right, this incident and this we have lattices, then since the magnitude of incident vector and reflected vector is same, so if taking this as radius, we draw one Ewald sphere, then since this radius is same, they both will lie on the sphere, and there may be some more points which lie on this sphere. If incident one we have taken and drawn this sphere, and we get the reflected one lying on this sphere, that means that satisfies the diffraction condition. It may sound a lot complicated right now, but this, what it tells in reciprocal space is that if I take incident vector with the magnitude 1 over lambda and draw this sphere, and the reflected one, because how we know where the reflected one goes, because it can go in all direction, and we had said that the rays which satisfies 2D sine theta is equal to n lambda condition, we only get those as constructive interference. So when the diffracted one lies on these spheres, for those only this condition is satisfied, and for those only we get the X-ray diffraction. This is how we define Bragg's condition in reciprocal space. Okay, and this is what we call Ewald sphere, and this concept was introduced by a person named Ewald. And this, if you use, when you use XRD for experiment, then you will see that how we check, okay, if this is my wavelength, then what all points I can, because all these points are actually in reciprocal space, all these points are, I told you, these are inverse of lambda, and their magnitude is inverse of the interplanar spacing. So here they are all inverse of interplanar spacing. So they are connected with our crystal planes. So there we get to see how which crystal planes we can get in the diffraction. So there these Ewald sphere are helpful. This is one example. Okay, I hope you understood Ewald sphere. Now to get the derivation for Bragg's law in reciprocal lattice space that I just now told you, I think although these, maybe I'm thinking of skipping this and focusing on something else actually. Yes, this is not very, and I think it's the derivation for Bragg's law in reciprocal space is there in lecture also. I think you guys can check it from there. So I'm skipping that because I have something important to discuss which was not properly covered in the lecture. So okay, I hope that definition, that derivation you can see from the main lecture. And yeah, now I want to talk about, so we talked how we have lattice arrangement in real space, and then we have lattice arrangement in reciprocal space. We have lattice vectors in real space, and then we have lattice vectors in reciprocal space. We have translation vector in real space, and then we have reciprocal lattice vector. Similar way, if I have a simple cubic crystal in real space, then what will I get from that simple cubic crystal that is in real space? In reciprocal space, what will it become? This is the question. So as we discussed that every primitive unit cell can be described by the translation vectors, right? So for simple cubic crystal, the translation vector, we can define it as So if this is my, let's say, either we can say A1 or let's keep it X, and this is Y, this is Z, right? Then my reciprocal A1 will be defined as X cap, A2 will be defined as Y cap, A3 will be defined as Z cap. And when we will do that, we have seen how to get that reciprocal space vector. So we will get the expression and we'll see that it's still SCC. Even in reciprocal space, it's SCC. Okay. You can see this in the lecture again, because here I want to focus on FCC and BCC, which were kind of not discussed thoroughly. So if you calculate A1 cross, okay, let us do one. So you know, for this the formula is A2 cross A3 cross divided by volume. Volume is what? It's A1 dot A2 cross A3. Here A1 is X dot and this is Y cross Z. Y cross Z is X, X dot X is 1, so volume is 1. And A2 cross this is X cap. That means A1 star is X cap after doing this. So similarly A2 star will get Y cap and A3 star will get Z cap. So even the what we say, this coefficient is same, and their XYZ were also perpendicular to each other. A1 star, A2 star, A3 star will also be perpendicular to each other, means the simple cubic structure in real space will remain same as simple cubic structure in reciprocal space. But what happens with when we talk about BCC? Okay, so one more slide. So in BCC, let's first draw the conventional unit cell again. Like just now we discussed that whenever we think about BCC, we always have in mind a unit cell with all the corners occupied by atoms and then one at the center, body center. This is the conventional BCC unit cell. But when we want to find out reciprocal lattice, reciprocal unit cell, then we need to know primitive unit cell in real space. Because clearly this is not primitive unit cell because it has more than one atom in the unit cell. So first we need to see that this is a conventional BCC cell and there are lots of infinite ways to generate a lattice. Any kind of lattice, if we like, it's difficult to draw 3D. So in 2D we know there are infinite number of ways to get a unit cell. Like I can say that this will translate in this direction and I'll get, or this will translate in this direction, or this will translate diagonally, or I can take another unit cell itself. This is not primitive, but it is still unit cell. And I'll say when this will translate, it will give me this. Or I can make something like this. So this and this are example of primitive. This is not primitive, but they are still, after repetition, will generate the whole lattice. So there are such innumerable ways of generating the whole lattice. So when we talk about BCC, this conventional unit cell, there are actually infinite number of ways to define even the lattice points in 3D also. But this is one way we usually use, and this is the conventional structure. So if we want to get primitive unit cell, then how to get that, we'll see. So in this BCC, I have a diagram already made so that I don't make not so straight lines. This in black line, these edges are the BCC conventional unit cell. How? Because all the corner atoms you see black dots, they are the atoms, and one atom is at the body center. Now this is A1, A2, A3. This is what? This is my lattice vectors. This A3 and then this A1 in this direction, right? And then I think this is A1, this is A2, this is A2 and this is A1, which parallelly we can translate it to anywhere. I hope now it's clear. You can take it here, you can take it here. Direction is what it's symbolizing, which is important. So what we see here is, if the center of the body, the atom, if I join on this corner, and this other corner, if I join it like this and then make parallel to it, so when I join, if I have a diagram, okay, let me try here. Although again we know the atoms are so big that they are almost touching each other, but so that the diagram is still easy to understand, we make the atom size of a point. So we have atoms on the corner, and the body center, and if I join this with this point, with the other point, and this other point, okay, I'm joining them, and now if I make parallel to this and parallel to this vector also, if I make, right, then I'll get this, and where these two are intersecting, there will be another point, another atom actually, that I want to show. When I join them and again take parallel to them, okay, where they are intersecting, there will be another point, and this point means this atom will be body center of the cube on the top of given cube. We know this is not isolated, right? It has innumerable cubes around it. So right, left, up, down, front, back. So where these two will meet, that will be body center of the atom at the cube at the top. If I draw a cube at the top, this point will be the body center of the top cube. Similarly, if I draw parallel to this here and parallel to this here, then actually why we get this? Because if you remember this triangle law of vector addition, if we have something like this, if we have one vector here, one vector here, then the final one we get like this, right? But if we have something like this, then we define it using parallelogram law of vector addition. We draw parallel to them and then we take this. So that is how it's like taking this resultant here, or this resultant here, or this resultant here. But anyway, so when we draw this or take resultant of these two joined, then we get the location of another atom. This will be body centered of the cube in the front. Similar way, when we will take resultant of this, it will be the location body center of the cube on the right of the already given cube. That means it has covered these three more cubes. Now if you see properly, this new cube that we have drawn, okay, this red one, all the atoms are only at the corner of this red cube. Although they are connecting all the body centers, this is also atom of body center atom of another cube. This is also joining the this is also body center of another cube. This is also body center of another cube. And this one corner of this red cube is also sitting at the body center of this black cube. So they are all connecting the body centers, but if you see, there is no atom sitting anywhere apart from the corners. That means this is a primitive body centered unit cell. Yeah. So this is how we generated this primitive BCC from conventional BCC. I hope it's clear. If it's not clear, please ask. I'll explain how again we did. So we took our conventional BCC and we joined the atom at the center with these three at the corners. Then we took the resultant by using parallelogram law of vector addition, and then they told us the location of other BCC atoms of other cubes, and while doing this we get this cube with 8 corners and only atom sitting on the corner, not inside or on the face or anywhere. So this is a primitive BCC. Now when we get primitive BCC, because I told you if I want to see my BCC will go and become what kind of unit cell in the reciprocal space, I need to start from primitive unit cell. So this is my primitive unit cell. Now what will be the translation vector or basis vector for this primitive unit cell? Now we don't have, to understand, now only consider this red one, and we need to find out what will be the translation vector for this primitive unit cell. This is what we have drawn. If you connect this, you can see the whole cube which is in this direction, and you will also see that they are not, although the A1, A2, A3 in this conventional unit cell were 90 degree, in this primitive unit cell they are not 90 degree, but they are primitive. Okay, so the translation vector, if you see how we get translation vector for BCC, is this A1. If we take this E1, E2, E3, okay, in the conventional unit cell we take this unit vectors as E1, E2, E3. Now we take the translation vector in terms of this. So what we'll get is this A1, how will reach A1? If I start, this is origin, let's take this corner as origin, and then this is in the center of the body, right? Like if I see the top view, I am taking origin with the body center atom, and my A1 is sitting here, right? So if I need to reach there, I need to move half. If the edge length is A, then I need to move A by 2. In which direction? E1 is towards front and I have to move back. That means I have to move A by 2 in the minus E1 direction. Minus E1 direction I have to move. So A1 is minus A by 2 is the magnitude. A by 2 is the magnitude and direction is minus E1. Instead of E1 we can take X, Y, Z or anything. Okay. So this is just the from conventional unit cell to primitive unit cell. So for conventional unit cell we had A1, A2, A3 as our lattice vectors. In primitive unit cell we have E1, E2, E3, and we are just making the relation between that A1, A2, A3 and E1, E2, E3. That's all we are doing. We are still in real space. Please keep in mind. So A1, A2, A3, let me write. A1, A2, A3 belongs to conventional unit cell, and E1, E2, E3 belongs to primitive BCC unit cell, but we are still in real space. So I'm just telling you the relation between A1, A2, A3 and E1, E2, E3. Okay, so when I moved A by 2 in minus E1 direction, I reached here. Then after that I reached here because it's in the body center. Then I'll move half a by 2 along a3 direction, right? Then I'll reach here. Half a by 2 I'll move along a3 direction, that is also e2. And then finally to reach a1 I'll move a by 2 along e3 direction, a by 2 along e3 direction. I hope this is clear. Like from this taking as origin, if I want to reach a1, because I want to define a1, I need to move a by 2 towards back minus e1. Then I have to move half a by 2 towards e2 direction, and then finally I have to move a by 2 towards along e3 direction, finally to reach my a1 vector. Okay, so this is the relation between a1 vector and even e2, e3 unit vectors of primitive lattice unit cell. Similarly, a2 of conventional unit cell, which is here. Okay, so from center if I start, I need to move a by 2 along e1. I need to move a by 2. Why a by 2? Because it is at the body center. So any edge is half of a for it, because the edge is a. Okay, so to reach a2, the atom needs to come a by 2 along e1, and then it reached the front face. Now it needs to move a by 2 towards this edge. So a by 2 towards this edge means minus e2 direction, and now it has reached here, halfway of this edge. Now finally to reach a2, it needs to move along e3 cap direction by a by 2. Okay, so this is another relation. So these a1, a2, a3 vectors will tell like my primitive BCC lattice vectors. Okay, and a3 cap will be, to reach a3, this will move a by 2 towards front, and then a3 is here, so it will need to move a by 2 towards e2, and then it needs to go down, because it's at the body center, it needs to go down. Right now it has reached here, it needs to go down to reach a3, means minus a by 2 down when parallel to e3. So this is the third relation. This is how a primitive lattice vector can be defined in real space for body-centered cubic lattice. I hope how we got this is clear now. And then later we'll see that, okay, this is the lattice vectors for BCC in real space, for primitive BCC in real space, how to get corresponding reciprocal lattice vector for these. Okay, or we can see that also actually. Yeah, so we already got our A1 for BCC. We are doing for BCC primitive unit cell. The lattice vectors were A1 was minus a by 2 E1 cap plus a by 2 E2 cap plus a by 3 E3 cap. If I take out all the a by 2, then it will be a by 2 minus E1 cap plus E2 cap plus E3 cap. Similarly for A2 vector, it will be A by 2. After taking out this, it will be E1 cap minus E2 cap plus E3 cap. And for A3, it will be A by 2 and E1 cap plus E2 cap minus E3 cap. So these were in real space BCC primitive lattice vectors or basis vectors. Now to construct reciprocal lattice vectors, A1 star, A2 star and A3 star, out of these we know the relation. We have to calculate volume, and then it will be, if it's A1, it will be A2 cross A3. Okay, first we need to find out the volume. So volume, we know the relation is A1 dot A2 cross A3. That means this is, we know cross product A1 dot, and cross product is taken like this, right? Here it will be A2 x component, A2 y component, A2 z component, A3 x component, A3 y component, and A3 z component. This is how we do, right? And when it's combined with dot product, then what we'll get is this A1 x component, A1 y component, A1 z component, and A2 x component, A2 y cap, A2 z cap, A3 x cap, A3 y cap, A3 z cap. And since this is a matrix, we need to find out the determinant, that we know how we do. Okay, so here what is our A1, A2, A3? These are this. So when I arrange in the matrix, I will get the volume as this. So this is minus A by 2, A by 2, A by 2. So like that. Okay. So it will be, first row will be filled by all the components of A1, which is minus A by 2, then A by 2, then A by 2. All the components of A2 vector, which is A by 2, minus A by 2 and A by 2. Then components of A3 vector, which is A by 2, A by 2 and minus A by 2. After taking out, after calculating all these, we know how we calculate, right? This is like minus A by 2, and then product of this, which will be A squared by 4 minus A squared by 4, okay, minus this A by 2, then this minus A squared by 4 minus A squared by 4 plus now this A by 2, A squared by 4. I hope you guys remember how to do matrix or how to find out determinant. This will be plus A squared by 4. So you see, this will be cancelled, this will be cancelled, we'll be left with this minus A by 2. This will be minus 2A squared by 4, minus minus plus, and 2 to cancel. A cubed by 4 is the volume. That's correct. Okay, so when and And when we finally find out A1 star, it will be A2 cross A3 divided by volume. After you will do the calculation, you will get this as 1 by A E2 cap plus E3 cap. Similarly for A2 star, when you will do the calculation of A3 cross A1 divided by the volume, you will get 1 by A E1 cap plus E3 cap. And for A3 star, we will get 1 by A E1 cap plus E3 cap. Now these are the reciprocal lattice vectors for when our real space, in real space we had BCC, and in reciprocal space what do we get? We get this. Right now you don't know what it is, but actually we'll see about FCC, and then you'll get to know that in reciprocal space these lattice vectors actually are denoting primitive FCC. This is very interesting that SCC changes, it doesn't change, it remains SCC in reciprocal space, but BCC in real space, the lattice vectors of BCC results in FCC in real space, and FCC in real space changes to BCC in reciprocal space. Okay, so this A1, A2, A3 that were primitive lattice vectors of BCC changes to this lattice vectors A1 star, A2 star, A3 star, which are actually FCC. How we know that? Because now let's see and check what will be the primitive lattice vector for FCC in real space, and then you will see these will be same. Okay, so yeah, so we did for BCC. Now let's do for FCC. So this is conventional FCC right now. Conventional FCC unit cell, because it's not primitive. As we can see, there are more than one atom in this unit cell. So this is just conventional FCC unit cell. If taking this one at the corner atom as the origin, I join these three phase centers by A1, A2, A3. Let's call them A1, A2, A3, the phase centers. Okay, I get something like this. Then again, I'll take the resultant by joining these sides. Okay, so I'll get something like this. These two will be joined, these two will be joined, and where they are reaching this atom, when I'm joining these A1, A2 here, it's reaching the face center atom of the top face. Then when I'll join A2, A3, I'll get the face center of the atom of the front face. Similarly, when I join these two, I'll reach the atom on the face center on the right side. And when I'll further join these others, I'll get the one at the back. So this is another unit cell. In the red one is primitive FCC unit cell. Okay, because all the face center atoms that were actually face center atoms for this black unit cell, which was conventional FCC unit cell, they all are on this primitive unit cell, but they are not inside, they are on the corner. So total contribution is still, you see this red cube, all the atoms are only on the corners. Okay, so this is making primitive FCC unit cell. And now if we define again, taking this as origin, if we define to reach A1, A2, A3, we see that we need to move half of the edge, that is A by 2, and then half up. If E1, E2, E3 are my basis vectors for this conventional unit cell, then A1, to reach A1, I need to move half, because this is again A, and this is cubic, so all are A. I need to move half along E2 direction. I need to move half along E2 direction. Then I need to go half up along E3 direction. Not half up. Yeah, half up to reach this. Because this atom is at the back face, so it is at the center of the face, so only half I need to move. Okay, and I've reached A1. For A2, again the origin is same, origin will always remain origin, and to reach A2 I need to move half at the front, that means along E1, then I need to go half along E3 and no movement along E2. For A3 I need to reach here, that is the bottom of this face. I need to go half front and half along E2. So these are the lattice vectors for FCC, primitive lattice vectors, and when I write it in simplified way, you will see this is the same expression that we had got when we calculated the reciprocal lattice vectors for BCC. So see, this is like A by 2 and E2 plus E3, E1 plus E3, E1 plus E2. This is what we had got here after calculation. Where did it go? Yeah, this. And the magnitude is not that important. Anyway, it just tells the length. But the structure is what we are talking about. So we have something in magnitude, and then E2 plus E3, E1 plus E3, E1 plus E3. This is what we got. So it is same as what we got for FCC. So that's why we were saying that BCC primitive in real space changes to FCC in real reciprocal space. And similarly, when we will calculate that FCC in real space, when we calculate reciprocal lattice vector for these, we will see they become the BCC lattice vectors. Okay, so this is one thing, because just a beginning, so that you guys can understand something that we cannot directly, by using our conventional unit cell, we won't be able to get these expressions for it is reciprocal lattice vector. So here I tried to explain you guys this, and then now we have some time, so I think we should move to solving some problems. Guys, for this at least, okay, let's just see when we'll calculate this. Also, one thing I wanted to tell is for BCC, for BCC, when we get this A1, A2, A3, another thing is this primitive unit cell, this magnitude. What do you think is the magnitude of this A1? This is A1 from the center of the cube to this corner. What is the length? What is the magnitude? And they all are same because they all are connected. These all corner atoms A1, A2, A1, A2 and A3 are connected with the body center. That means they all are at the same distance from this origin point or the center, body center atom. That means A1 is equal to A2 is equal to A3. But what is that magnitude? So as I said, this O is the body center atom, and we know that body diagonal of a cube we know what is the length, right? If the edge length of cube is A, then body diagonal is root 3A, and we had derived it in last week's session. So you can see there, face diagonal has root 2A, but body diagonal has the length of root 3 times A. Okay, and since it is like body diagonal will be from this corner to this corner, from A to B, but we want only this A to B will be the total body diagonal root 3a. O is in the mid of this whole length, because this AB, which is root 3a, is equal to AO plus OB, and we want to find out OB. So that will be half of AB. That means root 3a by 2. This will be the unit, this will be the magnitude of these vectors. And when we will take dot product of these lattice vectors a1 dot a2, and we know direction cosines, right? When we will do that, we will get the direction also between them, and we will see that these directions of primitive lattice vectors, they are all equal, but they are not 90 degree. In fact, they are 109.5 degrees. So that's why, although this we got a primitive BCC unit cell, but this is not orthogonal. They are not this A1, A2, A3 are not perpendicular to each other, but they are at angle 109.5 degree. Similarly, for FCC, this FCC primitive unit cell, okay, here you will see that what will be the magnitude. Again, since they all will be same, and the magnitude will be, I started from here, and the distance I'm getting at the same distance, right? A1, A2, A3, they are all at same distance, because they are all connecting the face centered atoms on the adjacent faces. So all this topic is relying more on visualization. You need to visualize, or you need to draw and then understand. Otherwise, it's hard to see what's going on. So all these magnitudes will be same, and since what you see this is corner, this is face center, and we know that face diagonal, if the edge length of this cube is A, then the face diagonal will be, length of face diagonal is root 2 times A, and here this A3 is in the center, so that means A3 magnitude will be half of this. That means A by root 2. This, and the angle here for this FCC primitive unit cell, the angle all are equal, and it's actually 60 degree. So this is one relation. Okay. Now I think with this, let's move on to doing some questions here. First question is the nearest neighbor distance in BCC structure. So the nearest neighbor distance in BCC structure. Oh, that is very easy actually. We know in BCC, again, this is very, we have at the center, and then we have on the corners, and we know, if I draw, we have atoms like this. On the body center, we have them joining, right? That means on the body center, they are the nearest, because on the edge, they have some gap. So nearest neighbor will be this atom and this atom. They are nearest to each other. And what is the distance between them? So body diagonal, as we said, body diagonal has length root 3 times A, if the edge length is A. Then these two atoms, what is the distance between them? As you can see, radius of this atom and radius of this atom. That means 2r is equal to the distance between these two atoms. So distance between these two atoms is 2r, but our answer is in terms of A. So what is the relation between A and R? For BCC we know 1r, 2r, 3r, 4r. We know, we have been doing it many times. For BCC, 4r is equal to root 3a. That means r is equal to root 3a divided by 4. So 2 times root 3a divided by 4. This will be root 3a by 2 is the distance between the nearest neighbor in BCC. Root 3a by 2 is the correct answer. Option A is correct. So you have to keep in mind the relation and how first it starts. You should know conventional BCC, how it looks, which are the touching atoms, and then what is the value of body diagonal, what is the value of phase diagonal. If you keep these things in mind, you will be able to solve these questions. Because if you start deriving the body diagonal length using all the Pythagoras theorem, then it will take, you will get to the answer, but it will take a lot of time. So by now at least you should remember that body diagonal length is this, okay, root 3a times. Okay. So next question is the fraction of volume unoccupied in the unit cell of BCC lattice. So we had done packing fraction. Something similar we have to do here, but here we have to find out the volume that is unoccupied in BCC unit cell. And when we talk about nothing is given, we usually take the conventional BCC. Okay, the fraction of volume unoccupied. So we know that in BCC there are total 2 atoms, total 1 in the corners and 1 in the body center. Also we know the relation in BCC is 4 radius of the atoms is equal to root 3 times A, the body diagonal. Just now we did, right? This was for BCC only. So we know the relation between radius and edge length. Now volume occupied by atoms in the unit cell, one atom will take like volume of sphere, because one atom, every atom is spherical, so volume of 2 atoms will be 2 times and this 4 by 3 pi r cube. This is the volume of one atom, and since we have 2 atoms in BCC, so this is the total volume taken by atoms. Now what is the total unit cell volume? Because yeah, I mean, I have this unit cell, I understand, with edge length A, but atoms are not completely there, right? There is at the body center, then all the corners, but there is some gap also. So I need to find out that unoccupied volume. So total volume of these 2 atoms will be this. Okay. Now total unit cell volume will be A cube. Now let's calculate this further by keeping the value of the relation between R and A, and then I'll keep the value here. Okay, so this further when I'll do uh, 2 times 4 by 3 pi, and R in terms of A, R will be root 3a by 4. Root 3a by 4 whole cube. Okay. When I solve this, this is cube. When I will solve this, this is 8 by 3 times pi times this is 3 root 3 a cube 464. Okay, this will be the total volume of 2 atoms, and total volume of unit cell is A cube. We need to find out the unoccupied. That means, so unoccupied volume means volume of unit cell minus volume of two atoms. Okay. So unoccupied volume will be volume of unit cell minus volume of two atom. But here actually we have to find out fraction of unoccupied volume. Since we have to find out fraction, that means we have to find out fraction of unoccupied volume, means volume of unit cell minus volume of these two atoms divided by volume of unit cell. Okay, so this will be this expression. We can little bit solve here. 3 cancel, 8, 8, 8. So it will be root 3 a cube pi by 8. Root 3 a cube pi by 8 minus volume, oh sorry. This is volume of unit cell. Volume of unit cell is a cube minus this is volume of atoms divided by volume of unit cell, which is a cube. And we'll do this in fraction. We'll get 1 minus pi root 3 by 8. Okay, in answer, okay, let's do it further. So it will be 8 minus pi root 3 by 8. 8 minus pi root 3 by 8. A is the correct answer. So you have to take care again that okay, it's BCC structure, then what will be the relation between the radius of atoms and the edge length, and then okay, that we have to find out unoccupied volume and that also fraction. So you have to take care of these keywords here and then it's pretty straightforward. Okay, the third question. The question is the mass of each atom of a metal is W. Okay, so the mass of each atom is W and its density is given by rho. If the metal is okay, so the structure is FCC. Quickly you should like visualize what is the relation in FCC, because on face of the cube we have atoms touching each other, right? So that means these are 4R, and what is the diagonal length? Since this is face diagonal, it is root 2A. Okay, this is the relation for FCC. We have to find out if the metal is FCC, then the side A, okay, anyway we took side A, of its conventional cubic cell is given by O. So what is the relation here between density and the conventional unit cell edge length? So we know that for a unit cell, the density is given by number of atoms or number of molecules multiplied by its atomic mass divided by cube, the volume of unit cell, and Avogadro number. This is the density of unit cell. Now here density is rho. Number of unit cell we directly not told, but we know it's FCC, means number of atoms. Here it's atoms, so number of atoms will be 4. In FCC we have 4 atoms per unit cell. Atomic mass we have not been told, it's W, just that. And then the volume we can find out because the edge length is A, so sorry, it will be A cube, and Avogadro number, let's keep it as Na. Okay, now we need to find out the value of A. Fine, that means we need to find out A cube, and I'll take all the these parameters on the right side, and unknown A cube I'll keep on the left side, and this will be 4 omega divided by Okay, one thing. Yeah, sorry, that's mistake I did. Then the formula atomic mass. Atomic mass, if you remember, atomic mass is given in gram per mole. Sorry, gram per mole. And in 1 mole there is Avogadro number of atoms. So that's why we divide using Na. That means the mass of atom is actually atomic mass divided by Avogadro number. So this whole atomic mass per Avogadro number is actually this mass W. Okay, and then if I just rewrite this thing is W, and that means AQ will be 4 omega divided by density. Now A will be 4 W divided by density whole 1 by 3. So the correct answer is 4 W divided by rho 1 by 3. This is the correct answer here. So this you need to keep in mind. Atomic mass is given in gram per mole, and 1 mole has Avogadro number of atoms in it. That's why we do divide. So if we have been given the mass, that means atomic mass divided by Avogadro number is our mass. Okay. And next question. The smallest distance between any two atoms in a FCC crystal, the smallest distance, if they are saying, that means they are talking about nearest neighbor, right? Because they will be nearest, and that's why the distance between them will be smallest. Anyways, so this is two different way of saying the same thing. The smallest distance between any two atoms, that is the nearest neighbor distance in FCC crystal, is 0.2. FCC crystal, we know the nearest neighbor is on the face diagonal. Phase diagonal length is root 2a and is equal to 4r. So here these two atoms are the nearest, and the distance between them is from the center of this atom to from the center of this atom. And what is the length? We know this whole phase diagonal is root 2a. Phase diagonal length is root 2a, and this is half of it, right? The distance between these atoms, distance between nearest neighbors, is half of it, means root 2a by 2, that is a by root 2. Okay, and they have given that the nearest neighbor distance is 0.2. Find the volume. So they have already given this is 0.2. So when I equate this, I will get A is equal to 0.2 times root 2. I have to find out volume of unit cube. That means it will be A cube, right? A cube will be this 0.2 times root 2 whole cube. This will be, let's do using calculator, and then 0.2 times root 2 is 0.282 it, and then when I take 0.0226 0.022624, the unit is in 0.2 nanometer. So this will be nanometer cube. 0.0226 nanometer cube is the correct answer. This was also pretty straightforward. Next question. Okay, find the angle between 111 direction and 100 direction in cubic lattice. This formula we had seen earlier, that how we find out the angle between two planes. Similarly, angle between two directions, the formula goes like this: cos theta is equal to h1 h2 plus k1 k2 plus l1 l2 divided by root of h1 square k1 square l1 square, okay, multiplied by h2 square k2 square l2 square. This is multiplication where h1 k1 l1, these are the HKL for this one direction, and H2, K2, L2 are direction Miller index for another direction. So here this is 111, this is 100. That means H1 is 1, K1 is 1, L1 is 1, H2 is 1, K2 is 0, L2 is 0. So when we'll put these values in this equation, we need to okay. So cos theta is equal to h1 h2. h1 is 1, h2 is 1. So this term will survive. This will become 0 because k2 is 0 and l2 is 0. Okay. So in the numerator we will have h1 h2, which is 1 divided by under root, here h1 square k1 square l1 square, so it will be root 3. It should not be this big actually. This first root will be root 3 and the next one will be h2 is 1, others are 0, so this will be root 1. This will be 1 over root 3. So cos theta is 1 over root 3. So theta, that is the angle between these two directions, will be cos inverse 1 over root 3. So 1 over root 3, when you will take cos inverse of this, then you will get the value of theta will be 54.73 degree. 54.73 degrees is the correct answer. Option C. Okay, next question. Metallic copper forms cubic crystal and lattice parameter is 0.36 nanometer. If the specific gravity of the copper, specific gravity means relative density. When we take it relative to water or something, so here you can take it as density. The density of copper is given 9.04. Oh, it's unitless because it's relative density, means they have taken density of the copper here and in ratio with density of usually water. So that's why it has, because density of water is 1 gram per cc. So that's why here it has become dimensionless. Okay. That means if in you want in unit, then you can keep gram per cc. And its atomic weight is 63.5. I think it should be in gram per mole. Then find out, usually whenever we say, right, that for oxygen the atomic weight is 16, for carbon atomic weight is 12. We don't put gram per mole, but that should be understood. Then find out the type of crystal structure. They are asking type of crystal structure. So we know to find out if it is SCC or BCC or FCC, we don't need the edge length, right? We don't care about edge length. But if somehow we get to know how many number of atoms are there in that unit cell, we can know if it's SCC, BCC or FCC, because in SCC there is total 1 atom, in BCC there are total 2 atoms, in FCC there are total 4 atoms. So if we get to know the total number of atoms in this unit cell, then we can tell which type of crystal structure this is. So let's find out. We have been given density, so our mind should work which relation we can use. We have a formula for density, right? Given by number of atoms, atomic mass divided by volume multiplied by Avogadro number. This relation we know. Now here density is given, which is 9.04. Number of atoms we don't know, in fact that is what we want to find out. A cube, this is atomic mass. Okay, atomic mass is given 63.5. Atomic mass, atomic mass is given. Atomic mass is given 63.5 gram per mole. I told you it should be understood. 63.5 gram per mole. Then we will divide it by Avogadro number. And volume of unit cell means A cube, and A also we have been given in nanometer. So here I want to find out N and L's. Rearranging this, I'll bring N, I'll keep N alone and everything on the other side, because N is what we need to find out. Then this expression will become 9.04 multiplied by this A cube. A is 0.36 nanometer, means 0.36 times 10 to the power minus 9 to the power 3 multiplied by Avogadro number, which is 6.023 into 10 to the power 23. Okay, so one thing, here we know atomic weight is in gram per mole. This is how we always give atomic weight, in gram per mole. So if this is in gram, that means our formula everything should be in CGS unit, right? That means this I should not convert into meter but into centimeter. In centimeter this will become 0.36 10 to the power minus 7 centimeter. In meter it will be 10 to the power minus 9, but in centimeter it will be 10 to the power minus 7 centimeter. So here I should better use this. Okay, this is in 1 mole, these are the number of atoms, divided by 63.5, the atomic weight. When we'll do this using calculator, 9.04 times 6.023 divided by 63.5 multiplied by 0.36, get 0.04 multiplied by all this 10 to the power minus 21, 10 to the power 23, because all the other things I have calculated using calculator, these powers I need to take care of. So this will be 10 to the power minus 21, this will be 10 to the power 23, and then the answer will become, this is 0, this will be 23 minus 21 means 10 to the power 2. So this will be 4 times, 4. Okay, so number of atom is 4. I got to know number of atom is 4, that means it is a FCC structure. F is the correct answer. Okay, now next. An orthorhombic crystal has primitive translations. Okay, these are the primitive translation. If a plane with Miller index 231 bar cuts an intercept of 1.21 angstrom along x-axis, find the length of intercept along y and z axis. Okay, so here we know that whenever we have like x, y, z, like let's say this is x, y, z, this is drawing, sorry, let me draw it. Okay, when we have this, we know whenever we define HKL plane, That HKL plane is intercepting on the x-axis how much? A by h. On the y-axis it intercepting B by k, and on z-axis it intercepts is C by L. This is the intercept, and that is why when we take reciprocal and put it into Miller index we get HKL. So the intercepts are these for the HKL plane. Okay, now here the HKL plane is given 2, 3, 1 bar. Okay, that means the intercept will become x-axis intercept. I told you it's A by h. Y-axis intercept it's B by k, and z-axis intercept it's C by L. If HKL is this, okay, that means the intercept ratio A by h, because this also, you remember, we take intercept and then we find out the common integer and reciprocal. So they are not exact values. They have been what we say, converted into whole number. So we need, actually they are ratio. So A by h, B by k, and C by L, these ratios we know is 2, 3 and 1 bar. That means since we have already been given A, B, C value, that means I can keep 1.21 divided by h is equal to 2. Okay, that means h is equal to 1.21 by 2. Okay, this is h. Similarly, B by k, B is 1.84, B by k, B is 1.84 divided by k is 3, and C by L, intercept on z axis, this is 1.97. 1.97 divided by L means 1 bar, means -1. So these values will be how much? These values will be 1.21 by, so these intercepts which are 2, 3, 1 bar, 2, 3, 1 bar is 1.21 by 2. No, it's not HK. It's A by H, B by K, C by L. Okay. Means A by H, B by K, C by L is 1.21 by 2. What will be the value? 1.21 divided by 2, or instead of 0.605. B by K is 1.84 divided by 3, that is 0.6133 is to actually we should not write it like this, I'm sorry, because we need to find out the intercept. Just a minute. Okay, so A by H, what I calculated here, 1.21 by 2. 1.21 1.21 by 2, b by k is 1.84 by 3, and c by l is 1.97 by minus 1. Okay, what it tells, we know HKL is 2, 3 minus 1. Okay, that means denominator is 2, 3 minus 1, and that means this is A, B, C. That means the intercept at A is 1.21, intercept at B is 1.84, intercept at C is 1.97. Okay, now, so we have been given that the intercept at x-axis is 1.21, and we have to find out intercept at y and z-axis. So intercept at x-axis is this, intercept at y-axis and z-axis is 1.84, 1.97 respectively. What did I do this right now? Intercept is, oh no, sorry, intercept is 1.84 by 3, which is 0.6133, this, and before the intercept is there's something. Just a minute. There's again something. Wait. Whenever we are given intercept, when we convert it to HKL, we take reciprocal and then we multiply it with a number. So here also what we have to do to get the intercept is to multiply by, given by, since it is like this, and we have been given that the intercept on x-axis is 1.21. That means the whole ratio we have to multiply by 2 to get the correct intercept. So then we will get 1.21, because this we do when we reduce it to whole number, right? That time we do this division. So the correct intercept I will get after, because one intercept I have told that at x-axis the intercept is 1.21. That means this 2 is extra that we may have used while converting it into Miller index. Now if I'll multiply by 2, sorry, the back calculation was getting difficult. Yeah. So now the answer will be this. So on x-axis the intercept is 1.21, on y-axis the intercept will be 2 times 1.84 divided by 3, which is 1.23 angstrom, and z-axis the intercept will be 2 times 1.97, which is minus 3.94 angstrom. This will be 1.21 angstrom intercept. Okay, so on y and z axis is 1.23 and minus 3.94. This is the correct answer. Yeah, so I mean, this is clear. The intercepts is A by H, B by K, C by L. And if you want to know how, because when we take intercepts, when we want to find out Miller index, we take the intercepts and then we drop these A, B, C. We only take the number, and then we take reciprocal, right? And this is how we get Miller index. So we have to do reverse. This is the intercept. These are the values given. We get them, and then here we need to take care that this intercept A by H is equal to 1.21 by 2. And we have been told that the intercept on x-axis is 1.21. That means this 2 in denominator is extra. So we will multiply the whole thing with 2 and then we will get the correct intercepts. Okay, next question. The spacing between successive 100 plane in NaCl is, okay, so D100. interplanar spacing is 2.82 angstrom. X-ray incident on the surface of the crystal is found to give rise to first order Bragg reflection, means this, at glancing angle of 8.8 degree, means theta is 8.8 degrees. Calculate the wavelength of X-rays. What is the Bragg's condition? 2d HKL 2d sine theta is equal to n lambda. 2 we know, d100 we know, 2.82 angstrom. Sine theta we know, 8.8 degrees. N we know 1. Lambda we need to find out. So this will be sine of 8.8 is 0.153 multiplied by 2 multiplied by 2.82 is 0.8628 angstrom lambda. This is the correct wavelength that we are using. One more question. For an NaCl crystal, the cell edge is 0.563 nanometer. The smallest angle at which Bragg reflection can occur corresponds to a set of plane of index. This is cell edge, and we know Bragg relation is 2d sine theta is equal to n lambda. Now, actually we know that whenever we get peaks, then for small order we get first, and then we get for next order, like 100 we will get first because this is 2 theta, right? And then we will get for 200, then we will get for 300 or 400. So for smallest angle means here. So for n is equal to 1, n is equal to 1, that is first order diffraction peak we will get for the smaller angle. So this one thing is done. Then with this expression, lambda is constant, whatever we are using. Then d for that interplanar spacing is also same. Only thing that can change is this theta. Okay. Now this theta, this will be n lambda by 2d, and because we have taken n is equal to 1, it will be lambda by 2d. Now this d, since it's a cubic cell, this d will be a over under root h square plus k square plus l square. For a cubic unit cell, the interplanar spacing between HKL plane is given by this. Substituting that here, h square plus k square plus l square, this will give sine theta. Now we know that sine theta, like theta, can go from 0 degree to 360 degree or 0 to 2 pi, and as for sine 0, for theta is equal to 0, sine 0 is 0, for theta is equal to, as the theta value increases, sine theta also increases. That means if I want the minimum value of theta, that means the minimum value of sine theta. That means the minimum value on the right hand side. Okay, I did a mistake here. This d is this, means 2 multiplied by a upon this, means this will be lambda multiplied by h square plus k square plus l square divided by 2a. If I want theta to be smallest, sine theta will be smallest, and sine theta will be smallest means this HKL, because a is constant, lambda is constant, HKL is the only thing that can change. So HKL, if it will be minimum, then sine theta will be minimum, and HKL minimum can be for 100 or 010 or 001. This is the minimum. If I go 110, then it will be root 2. If it will be 100, then it will be root 1. So only for 100 or 010 or 001, only for these possible, or minus 1 of course, they are all family planes, it will give the minimum value. So from this relation we understand the question was smallest angle we need to find out for which the Bragg reflection corresponds to set of plane. At what smallest angle we can get the planes? to get the smallest angle, we see here mathematically to get the smallest theta, the sine theta can be smallest. That means on the right hand side also the value how it can be smallest when this HKL combination is the smallest. That means the minimum possible HKL here is 100. Okay, because anything else and then it will increase. So this is the correct answer. Okay, so only these many questions this time, and if there's no more question then the time's also up. So as a quick review, what we did in this class, we understood what is reciprocal lattice, what are reciprocal unit cell, how we get reciprocal lattice vectors that we define on the basis of real lattice space vectors. Okay, they are related and we define their relation, and we define how we calculate reciprocal lattice vector, and we also saw that for what is Evart's sphere, what is Bragg's law and reciprocal lattice space, this you can watch in the lecture, otherwise we didn't have much time. And then we saw how SCC in real space remains SCC in reciprocal space, whereas BCC in real space becomes FCC in reciprocal space, and vice versa. And then we did these questions, right? Okay, so there is no more question. I'll stop the recording.